So, excuse me, may I ask you for attention? We are going to have the short presentations now. The first presentation is going to be given by Saurav from University of North Carolina. So please, can you start? You have 7 minutes, so please keep the time limit.
Thank you for the introduction. I'm Saurav Agarwal from University of North Carolina at Charlotte, and I would be talking about simultaneous optimization of assignments and goal formation for multiple robots. So let's say we have an initial formation on the left, and we want to go to the desired formation on the right, which is in a star shape. So sorry? Okay, is it better? Now? Okay, I'll try to be louder. So the first question is which robot goes to which location in the desired formation. So this is the unlabeled problem that we discussed in the morning. And then the next question is the variable formation. That is, where should be the goal formation be formed? So let's say if we knew which robot should go to which location, which is the labeled problem, then the question is where should the goal formation be formed? And then we can also ask what should be the size of the goal formation. So should it be really small, should it be large? And then we have an optimization problem that we would want to solve. So what we looked at is how to solve all these three problems at the same time simultaneously. Previously, the individual problems have been looked into, but we wanted to solve these problems together. So for this small example, we have the orange lines, which is the optimal goal formation that the algorithm had computed. So a mathematical description of the optimization problem is given over here. So we want to minimize the summation of the costs. And over here, the xij's are the assignment variables. So if we have x2, 3 equals to 1, that means robot 2 is assigned to goal position 3. So this is exactly the linear sum assignment problem that we saw in the morning. So for a standard assignment problem, we have theCij's as constants. But over here, when we have the variable goal formation included, then theCij's are no longer constants. They are functions of the formation parameters. Moreover, when we consider sum of square distances, then theseCij's are not even linear. So for a linear sum assignment problem, which we can solve using the Hungarian algorithm, theseCij's need to be constants. But over here, it's not true. So how do we solve it? So in order to solve it, we first looked at the naive method, which is just enumerating all the possible assignments, which is n factorial, and then looking at the structure of the problem. So over here, just for the scale parameter, we are looking at the cost as sum of square distances. So we can immediately see that there is a structure to the problem. First thing to notice is that the cost curves are convex. And the next thing is that they do not intersect with each other. So we were able to prove this mathematically for the general case. And even when we have the location parameter included, we found that the objective function is quadratic in the location parameter and also the scale parameter. And then we have the term inside the double summation, which is independent of the scale and the location parameter. And these Kij's are functions of the initial formation and the desired shape. So what this enables us to do is separate out the assignment problem and the goal formation problem. So looking back at the mathematical formulation, now instead ofCij's, we have Kij's, which are the pseudo cost, and they are still constants. So we are able to prove that the optimal assignment for a given initial formation and a desired shape is invariant and independent of the goal formation scale or translation parameters. So what this means is that if you recall the Intel videos which we saw previously, is that we have the desired shape and we don't need to decide where should the final goal formation be formed in the sky and what should be the size of the final goal formation. The algorithm will do it for ourselves. And simultaneously, it would also compute which robot should go to which location. And so we saw the concurrent trajectory planning slides in the morning. And over there, the robots were moving in a straight line, and the trajectories were guaranteed to be collision-free. So we use the same theorem and build over it. So over here, we have 600 robots, and the initial formation is in a rectangular grid. It goes to form the letters UNCC and finally the letters of ICRA. So you'll see that the robots are moving all in a straight line, and they also start simultaneously and reach their goal position simultaneously. And it is not necessary that the robots travel at a constant velocity, but it is necessary that the trajectory parameterization function is the same for all the robots. So now it's going to form the letters ICRA. So in the next example, we have 200 robots, where the robots are changing formation from cylinder to sphere to pass through a narrow opening. And over here, what we have done is we have also included constraints so that the scale parameters are such that the final goal formation fits within the whole of the wall. And also, we have given a constraint on where should the formation be formed, because we don't want the formation to be beyond the wall. So again, the robots start simultaneously and reach their goal position simultaneously. And finally, I have a simulation of 15 robots. So this is not the simulation, this is actual robots moving. And I can take questions while the video is playing. Questions?
Yeah, thank you. Do you have some questions? If not, let's.
Hi, thank you. It's a quick question. So here on all your simulations, you had some minimal velocity, right? So could you, I know, maybe say relatively what the maximum velocity of formation, like the maximum speed when the formation was achieved, you got?
So the velocity would be based on so the maximum velocity for any robot would be based on their distances. So based on what is the maximum largest distance, and the velocity would be curved according to that. So not all the robots are moving at the same velocity, they are moving at different velocities. Sorry, I didn't get your question. So right now, we haven't handled such situation where two robots cannot stay together, but there is an assumption that the minimum distance between two robots initially is 2√2r, which we also saw in the morning with the concurrent trajectory planning and assignment.
That's all. And I will ask André from University of Coimbra to give us talk about cooperative field robotics systems.
So, everyone can hear me, right? Yes. Thank you. So, my name is André Araújo. I'm from Portugal, from the University of Coimbra. Today, this presentation, I will focus more in the project that I am involved, also including my PhD work plan, because I started recently my PhD in January. So at the moment, this is my main idea, okay, that I want to use a multi-constraint, a decentralized multi-robot motion coordination. I didn't call formation control because I don't want to go to I want to create an abstraction layer on that to create a independency, because I don't want to focus in the kinematics or the physics of the agents. For example, if it is an aerial, or if it's aquatic, or if it's a ground robot. So I will try to create a distributed leader-follower approach, okay, but by assign like the leader will not be fixed leader. I want to create like a elected leader, follower, based on, for example, the task overload and those kind of metrics. And I also want to use optimization, robotic direct particle swarm optimization for parameter optimizations in the whole system. I will in the next slides, I will present the project where this specific work plan, the PhD work plan, will be applied. Okay. Now I will present the lab. So our lab at the moment, mobile robotics lab, we have 25 people working there. We are in this specific lab. We are focusing in cooperative perception control, multi-sensory perception, human-machine interaction, and hardware for Bayesian computing. Besides the mobile robotics in the institution, we also have in Porto and in Lisbon is like a group of laboratories. We also focus in computer vision, field robotics, health technology, intelligent control, and cognitive systems. Among other projects in mobile robotics, again, we are working mainly in social robotics, focusing in elderly physical activity promotion, social motion simulation, cognitive simulation. Then, following up the same trend of social robotics, this is the new project that we have in lab. It's a Iberic cooperation. Basically, they want to integrate also EOT and to promote the rehabilitation and social aware integration in the environments, like home environments. I'm not particularly involved in this project, but I can, if you have interest, I can forward to the correct person. Besides social robotics, we have a cooperative multi-robot system, patrolling. We will see after this project that it starts in 2011. In the company that I will tell you in some minutes, we put this solution in a real application scenario for a real application commercial solution. Okay. So here we can see some graphs of, and in that video of the real experiments in our lab using multiple robotics. Multiple robots, sharing the same graph with the algorithm of patrolling running on the back force. So besides PhD students, I'm one of the co-founders and the CTO of the startup called Engenharios. We founded in 2014. We mainly focus in research and technological development, and we have two focus at this moment. We have robotics and sports science focus in this moment. We have several solutions. Here you can see the roadmap of the company since 2014. We won a tender, a public tender. Basically, the university want to acquire some specific equipment to use in the lab. So we start from that point, and from that one, we achieve now, in 5 years, we have 4 robotics products, 3 for sports products, one national trainer, 2 P2020 R&D projects, robotic project. P2020 is it's similar to H2020, but specific for the country, for Portugal. Okay, and one R&D department that we are working on this moment. So, if you remember the patrolling system, we create a national funding project. It's called STOP. Okay, and basic STOPs. It's composed by a team of robots. Okay, in this specific application, it was for end user. You have a large surface, a large area to cover, and we deploy 3 robots. And what this system do, basically, patrolling, do the patrolling cycles. It's able to detect people. Also can detect for extinguishers if they are in the position of their obstruction. The doors, if they one door, if it should be closed and somehow it's open, or else the windows. And if you find out something that should not be there, you will report to the security team and do that warning. 2 weeks ago, we deployed this system for 100 hours. Okay, a long-term experiment. It was funny to find out issues that you will understand it with the time. That long-term experiments will tend to appear new issues that we don't have in the long-term experiments. It was interesting to see the amount of in the continuance of this project, we have a partnership now with Ocean Securities. We in October will deploy this system in the supermarkets that they use. They have, so it will start in Portugal, and in one year we want to have in 5 supermarkets that they possess. Another promising challenge project that we have recently, it's called Safe Fire. Basically, in Portugal we have a lot of fire outbreaks. So what we intend here is to create a system to clean, to avoid fires in the forest. To be quickly, so we have a team of aerial robots, UAVs in this case. We have a ground unity, and basically the UAVs will be deployed in a marsupial way, and they will be used for mapping and mapping the localization. So here, my PhD will apply directly on this topic, information control, because it's a common issue that we have in this project. The other project that is also going, it's specific for a customer. So basically, we have a team in similar analogy with the same fire. We have this project that we have a team of under surface platforms, okay, and then we have one underwater platform, and basically it will be used for localization. Basically, with the surface platforms, you want to emulate the satellites, and for that, the surface platforms should shape it to create the ideal conditions to triangulation, multilateration methods to run. So basically, you have to create a shape to help to localize the underwater platform. And if you are interested, we can talk an hour later, because 7 minutes, and I reach 9. Sorry.
Yeah, no problem. Thank you. So we have time only for one really fast question. And if there is no question, we can skip into another presenter. given by Filippo from University of Modena and Reggio Emilia. The talk will be about robotic pushing, and Filippo, please try to be within the 7 minutes because we are already delayed and some food is waiting for us. So.
Okay, can you hear me? Okay. So, thank you. And I'm Filippo Bertoncelli from the University of Modena Reggio Emilia, and I will talk about this thing called non-prehensile manipulation. First, non-prehensile manipulation is every kind of manipulation that's not done by grasping an object, so constraining the motion of the object with the end effector of the robot. So basically, like ping pong battling in the ping pong robot, or holding the door and opening the door as the Spot Mini robot is doing. But, of course, classical is a little bit more traditional, since we have opposable thumbs, and that's how we grab things. Non-prehensile manipulation science, it's a little bit more new research with respect to traditional grasping, has been approached by dividing it in 6 different types of manipulation. There's non-prehensile throwing, non-prehensile catching, that's done by matching the speed of the object you want to catch without grasping it. Batting is kind of a conjunction with the two, because you need to consider also the impact dynamics for sending the object where you want to go. Pushing, that's while you push an object across a table, across the floor, to bring it into a position, a desired position. Rolling is when you make the object roll on a position, or even on the end effector of the robot, so to have it reach desired orientation. And sliding is a little bit more complex to show, but imagine just by tipping the surface the object is on, to have it slide down because of gravity. And my field is actually robotic pushing, and this is a simulation of a single robot pushing a square object to the desired position. And here in particular we researched a controller for the robot to avoid the wheel slip for the wheel. So right now, while the robot is manipulating the object, the wheels are, there's a constraint applied in nonlinear model predictive control that avoids the wheel slip on the robot. And it was presented a few weeks ago at the Intelligent Autonomous Vehicles in Gdansk. And let's see. Now, the progress for this work is to consider the interaction directly with the object we are trying to manipulate. So we are introducing a new level of constraints on the robot motion and the object motion, so that the object, while being pushed, is kept like the whole system, robot plus object, moves like a rigid body. So that's the first thing we want to introduce in this field of research. And the next part will be, of course, multi-robot pushing. So to tackle the case when the object you want to push, it's either too heavy or too big for a single robot to push it. So this is why I'm here, basically, for multi-robot pushing. And was I quick enough?
Yes. Thank you very much. So we have now time for questions because you used only 4 minutes. So do you have some question regarding the box pushing? If not, let's continue with another presentation. Taras will tell us something about state observers in applications to vehicle dynamics.
Hello, my name is Borovets and I am a PhD student at Filippo National University in Ukraine. Today I'm going to give a short presentation about my study, and the name of my study is Agile Tire Mobility Controls, and this study is made with collaboration with Alabama University at Birmingham, USA. And the objective of my study is off-road vehicles, unmanned off-road vehicle, which can be considered as multi-agent systems, which consist of 4 elements, which we will name as open-link locomotion model. These elements includes wheel, suspension systems, wheel, suspension systems, and electrical drive. The objective is to develop control systems which will control this electrical drive, this open-link locomotion model, in order to satisfy a safe behavior of vehicles, safe moving vehicles without immobilizing of vehicle, without uncontrolled situations. So, in details, we can describe our locomotion model by next figures. Here we have suspensions, wheel, electrical drives, control systems, braking system, vehicle frames, and we need to remember that this open-link locomotion model is connected to each another open-link locomotion by frames, and that are connected by control systems that which can build as master-slaves control systems. So, the goal of our study is to develop control systems which will satisfy some mobility performance of our vehicles. In order to investigate mobility performance, we need to determine some index which will say us how good we moving under unpredictable terrain conditions. In this case, we use wheel mobility index, and in order to determine this mobility index, in order to put each mobility index in control system, we need to know about different vehicle states, dynamics of vehicle states, so that our research groups are divided into 3 groups which collaborate with each other to develop these control systems. We investigate real-time control systems, and for that we also develop sensors which get us reliable measurements such as torque measurements, velocity measurements, rotational velocity measurements, etc. And sometimes, as we know, sometimes we cannot measure some states due to technical or economical reasons. We need to use some techniques that is named as state observers. So, at first, I will say about sensor designs, and the main goal is to develop sensors which give continuous signals And it's very important because when we consider small time periods, we need to remember that discrete sensors give measurements with some time delays, and in order to avoid this time delay, we developed sensors which consist vane, shafts, and magnetics and Hall sensors, and a shape of vane satisfies a different area between magnet and sensors, and when vane is rotating, we obtained different continuous signals which are related to angular velocity of wheel. The next point is real-time controllers, and in order to design this real-time control, we investigate reinforcement learning algorithms such as deep learning, DDPG, and another. For that, we built mathematical models, and now we investigate mathematical models and try to learn our algorithms to satisfy desired velocity profiles, desired wheel mobility index, mobility performance, and under unpredictable terrain conditions. When we have investigated these objects, it was revealed that there are some states that cannot be measured directly, such as torque, wheel torques, because sometimes we cannot join these sensors to shafts, and also normal reactions that act in oppositive to load. And we need to know about normal reaction, and we need to develop algorithms such as state observers. In our study, we use four next state observers that were compared between, such as Lundberg observer, stunted Kalman filter, unstunted Kalman filter, and particle filters. We use a cascade scheme in order to avoid observation problems and also made tuning procedure more simpler. And we developed this for normal dynamics, vertical dynamics of open link locomotion, and for rotational dynamics of open link locomotion model. And using these algorithms, we can determine these two dynamics and state of these two dynamics. So in order to determine how our observers influence control systems, we investigate control system without observers with assumed ideal sensors, and for systems when observer were equipped, and it was investigated that observer make our control system more reliable because they can give information about unknown states and also filtering signals from sensors. This result is for torque estimation, and here we can see that observer give precise results. The same results were obtained for normal reaction estimations, and here we can see that observer is influence and control loop systems, however, is not bigger and satisfies desired velocity profiles. So you can see the next list of conclusions, and thank you for your attention.
Thank you for the talk. I will ask another presenter, and in the meantime, if you have some question, you can ask.
Yes, it's measuring index that can say you how good you're moving under unprediction conditions. And when you have 100% of mobility index, it means that your moving is good. When your wheel mobility index close to 0, it means that you have your moving is not better and you can immobilize right now.
Like, do you mean like the wheel is stuck, basically? I mean, if the wheel is having a lot of resistance against it, is that what you mean by having a low mobility index?
When you have, yes, when you have low mobility index, it means that you have worse frictions, and yes, and maybe you're moving under snow or medium or another terrain profile size.
More questions?
Thank you for your presentation. So the question is about multi-agent in your title. So you're assuming that 4 wheels are multi-agent, right?
Yeah.
So I just want to differentiate, for example, control surfaces on airplane is not considered as a multi-agent system. So can you just elaborate a little bit on that?
Yes, we have 4 agents, and we need to control these 4 agents in order to satisfy the same slippage. Under
They all control
path.
separately from the separate.
Yes, we control separate, but we have masters, and these masters control these slaves in order to satisfy the same wheel mobility index under for each wheel.
So please, Nicolas from University of Technology of Compiègne, where it is? In France. Okay, sorry, I don't know this. The talk is going to be cultural organization in robotic swarms.
Thanks. Okay. Hello, everyone. So my name is Nicolas Cambier. Today I will be talking about cultural organization in robotic swarms. And I'm trying to make this work. So it all starts with communication. So as we've seen today, communication is of paramount importance to swarm robotics. It's usually local and really simple. Usually we just transmit the state of the robots, such as the pose, or eventually its opinion as in a series of choices. Usually it's designed manually, so we don't really have a lot of possible information to send. And it's pre-designed, so it means that it can't adapt to the environment. As in swarm robotics, we want resilient controllers. We would like to evolve these communications in order to make them adapt to the environment. So there are some works in swarm robotics that use biological evolution, because obviously it's an optimization tool that's really used a lot. But even then, we still have communications that are more akin to signaling, so again, really simple states. And we would like something that is more comparable to human language. So I had a look in the state of the art in linguistics. And I realized that besides biology, there is a big factor in the development of language and in the complexity of language, it's cultural evolution. And also in linguistics, there are a lot of computational models to test different hypotheses with regard to the evolution of language. So we had tools that we can readily import to our swarm robots. And the tool I'm using in my thesis is language games. And it shows how a lexicon can appear through cultural evolution. So it's by self-organization. The robots communicate and they agree on some words to define some topics. The language game I'm using in my thesis is the naming game, so it's the simplest one of them all because you only have one topic and the swarm or the population in general only has to agree on the word to design this topic. To do that, the robots can have 2 roles. There are either the speaker, so it's the dude on the right, and the hearer, which are the robots on the left. And all of them have a lexicon, so it's kind of a dictionary. Except every word in this dictionary is
for the same topic. And we want the lexicon to reduce to one single word and to be that this word is the same in all the lexicons. So to do that, the speaker chooses a random word from the lexicon, and then it broadcasts it to the other robots. There are a lot of variations in the naming game, but this is the simplest version and the one that is more useful for some robotics, because in some robotics, usually you don't have directed communication. You can only broadcast, so this is really like the best we can have. And then the hearers, they receive that word, and if the word is already in the lexicon, the game is a success, so it's the case above. And if the word is not in the lexicon, it's a failure, it goes below. In the case of success, we reduce the lexicon to only one word, and in the case of failure, we just add the word to the lexicon. So with this really simple protocol, the whole population should converge, and it's proven mathematically will converge to one single word. Now, we want to import that into swarm robotics and into a swarm robotic behavior. So we choose aggregation, which is really the most basic swarm robotics behavior you can imagine, but also a really important one, because obviously there are a lot of tasks where you need the whole swarm to gather in the same place, and that's what aggregation does. There are different ways to program aggregation, but a really simple way is just to use a probabilistic finite state machine, and basically the robots can only walk randomly or stay in the aggregate, and the probability to go from one state to the other is given by the functions on the right. And you have parameters to regulate the steepness of the function. So if you have really high parameters, the robots will tend to join aggregates but not leave, which will create a lot of small clusters. And if you have a high probability, low parameters, then you will probably walk a lot of the time and you won't ever form aggregates. So the goal is to find a trade-off between the two. And it's actually quite complicated, and as the scale of the swarm increases, it becomes more and more complicated. So you can see that even the optimal parameters, because you have a range of parameters, the optimal parameters do not perform well at all if you have as few as 100 robots. Okay, and now the question is, how do we link the naming game with aggregation? The first thing we tried is to use the successes of the naming game. So remember, it was the moment where we reduced the lexicon to one. Oh yeah, sorry, I forgot something here. So here, the function in the x-axis, it's the size of the neighborhood. So the idea is that the more neighborhood you have, the least chances you have to leave the aggregates. So the bigger aggregates are more stable than the lower aggregates. Okay, so back to this. So instead of counting the size of the neighborhood, we count the success of the naming game. And there are a lot of interesting things that happen, but the most interesting is showed below. What we see here is that depending on the parameter, so if we increase the parameter, instead of aggregating each time as one aggregate, they form a variable number of clusters that is pretty reliably the same. For one parameter, you have the same parameter. Even more interesting, the naming game, instead of converging to one word, converges to one word for each different cluster. So obviously, this is application for coalition formation and task assignments. But then this gives me another idea. This idea was, what happens if we use the words of the naming game as an encoding of the parameters? So, as I said, we have different parameters, and we encoded these parameters in 24 bits, so we have millions of possibilities, and we use the words of the naming game to set the controllers. And what happens then, and we also have some mutations to create new parameters in the naming game. And what happens is that with quite a high mutation, actually, so it's the green curves, well, the cultural evolution of the aggregation outperforms the optimal of the parameters. So the red line is supposed to be the best performance you could ever get with aggregation, but if you have some cultural evolution, you can do better than that. So why does it happen? Well, I will show you. Is that? Wait. How do I? Sorry. Yeah. I knew there was a keyboard. Yeah, okay, so I have a small simulation that I can show you. So, yeah. Wait, I'll start at the beginning. So at the start, every agent has a different word. The words are coded as colors, so it's more obvious to you. And then we play this. So the goal is to gather. So at the start, there is a lot of small clusters with different words. And then actually there are mutations that appear. And if the mutations are bad and pushes you to leave, well, you leave and you don't infect the rest of the cluster normally. So this means that there is a selection of higher parameters that pushes for more stable clusters. But also, if you are in a small cluster, even if you left immediately, there is some small infection and the word is not erased immediately and can contaminate the whole cluster, which pushes it to actually disband, and then to go eventually in bigger clusters, which are able to drown out the bad mutations. So basically, the naming game reinforces the dynamic that we would expect from aggregation and create almost perfect aggregation compared to the fixed aggregation where we have to find a trade-off. Thank you.
Thank you, Nicolas. I will ask another presenter, and in the meantime, if you have some questions. Yes, if there is no question, then Tomáš can prepare his talk. So with Nicolas' presentation, we have finished the, let's say, theoretical part of today's summer school, and now we are going to have a bit more practical part. Tomáš will tell you something about our system, which is important for you because the system will be used for the final experiments on Friday. So you will be learning how to use our system in ROS, and Tomáš will present us some implementation details. After that, you will be split into the groups, as I mentioned, and go to discuss details of particular topics.